In this video, we want to discuss how you can use information on dependencies to find parallel tasks that can execute multiple iterations. The first step is to analyze loop-carried dependencies. You've got to enforce true dependencies. That is, if one statement provides an input to the next statement, the first statement needs to be done before the second statement takes up. But if you have output dependencies or anti-dependencies, you may be able to remove them via aliasing, as we'll see later on. But remember that true dependencies always need to be enforced. And where dependencies are not present, there are opportunities for parallelism. Take a look at example 1. This is a singly nested loop that hops through a one-dimensional array, setting each element equal to the element that was 2 places before it in the array. So the loop looks like this. The loop dependence graph looks like this. You see a dependence between the second iteration and the 0th iteration, the third iteration and the first iteration, second iteration and the fourth iteration, and so forth. So we can divide the loop into 2 parallel tasks, one that does the even iterations and one that does the odd iterations. Each even iteration needs to finish before the even iteration that follows it, and ditto for the odd iterations, but the odd iterations don't need to wait for the even iterations or vice versa, because the odd iterations and even iterations don't share any data. Example 2 is a doubly nested loop where in each row an element is set equal to the element before it in that same row plus 1. So we see that the dependencies are all in the horizontal direction here. You have iteration 1, 2 depending on iteration 1, 1, and so forth up to iteration 1n. But nothing in the second row depends on anything in the first row. So I could ask you, how many parallel tasks are there here? And you would take a look and say, well, how many of these chains do we have that don't have any dependencies on each other? And that would be n, because there's one of these parallel tasks per iteration of the outer loop. Now in example 3, we have our familiar 4-point iteration, where each element of the grid is set equal to the sum of all the elements surrounding it, above and below and on either side. Here we want to identify which nodes are not dependent on each other. But notice that, as we saw in the last video, there's a true and an anti-dependence from node 1, 1 to node 1, 2 and to node 2, 1, etc. So there are lots of dependencies here. However, in each anti-diagonal, in fact that's shown here, you can see that no nodes in an anti-diagonal are dependent upon each other because no one is an input to the calculation at any of the other nodes in the anti-diagonal. So how do we solve this problem, or how can we parallelize it? Well, we need to write code to iterate over the anti-diagonals. So we do that first of all by calculating the number of anti-diagonals, which is a relatively simple calculation, and then we loop over the anti-diagonals, first of all calculating the number of points in the current anti-diagonal, and then we can do a for all loop, that is with processors working in parallel, on all of the points of the current anti-diagonal. So here's how we do that. If I is less than n, in other words, if we are in one of the first n anti-diagonals, the number of points in the anti-diagonal is simply I, and the anti-diagonal starts at row I, column I. But if we're beyond that, then we're dealing with one of these anti-diagonals that doesn't begin at the left-hand side of the grid, and there the number of points is 2n minus I. And I think you can see that as I increases, the number of points in the anti-diagonal will decrease. It starts at row n, they all start at the bottom row, and they start at a column that's offset from the right edge by the value of I. And then, as we iterate over the anti-diagonal, we simply go through the anti-diagonal at each step, decrementing the row number because we're moving up a row, but incrementing the column number because we're moving right by one column.